Hello everyone, my name is Abdulkerim Ahmet. Today me and my team will present a topic that is very important in operating system, and it's called the role of system calls in secure process management. In this presentation we will explain what are system calls, why they are important for system security, how process management system calls work, and also how attackers can abuse this part of the OS. We will also talk about real attacks and modern defenses. So let's begin with the basics. What system calls are? System calls are basically the communication channel between application and the operating system. A normal program cannot do important things directly. For example, it cannot open files, cannot read the disk, cannot create a new process, and cannot access memory or hardware by itself. So the program have to ask the operating system to do these things for it, and this request is what we call system call. System calls are very important because they interact with the kernel, which is the most powerful and the most sensitive part of the operating system. If something goes wrong, here the whole system can be attacked, and that's why learning about system calls is not only useful for programming, it's also useful for cybersecurity. Why system call security matters? One of the best ways to understand the importance of system call security is to look at real attack. A very famous example is the dirty cow. Dirty cow was caused by a race condition inside the kernel. A race condition means the system checks something, but before it uses that result, the value secretly changes. In dirty cow, unauthorized users was able to write to files that were supposed to be read-only. So this was a huge security problem. This example shows something very important. Even a tiny mistake in system call handling can give an attacker full control of your system. This is why system calls are considered one of the most dangerous attack surfaces in an OS. System call architecture. Now let's understand how system calls work from an architecture point of view. The operating system has two main areas: user space, where normal program run, kernel space, where the OS runs with full privilege. Program and user space has limited permissions. They cannot touch hardware or critical resources directly. So when a program needs to do something, it sends the request to the kernel using a system call. This request triggers something called mode switch. The CPU switches from user mode to kernel mode to safely execute the system call. This flow from user space to kernel space must be controlled by a validated, if not secure, attacks can break into the kernel. If it is not secure, attackers can use it to break into the kernel. Steps of system calls. Let's take a look at what actually happens step by step when a system call is made. Step 1. The user program calls a library function like open or write. This function prepares system call. Step 2. A special instruction triggers a trap and switches to kernel mode. This gives the OS full control. The kernel checks everything: the arguments, the memory address, the permissions, and whether the process is allowed to do operation. This validation step is extremely important for security. After finishing the operation, the kernel returns to user mode and switches back to user mode. This whole process happens in microseconds, but it must always be correct and secure.
Hello everyone, I am Faris Fadli and I will continue. Process moved through different states: new, ready, running, waiting, terminated. The operating system uses system calls to move process between these stages. So, secure process management depends directly on secure system calls. These are the most important system calls: fork, exec, wait, exit, clone, created threads, or custom process, because these calls control how programs start and change. Attackers often target them. UID, GID, plus access control. Each process has a user ID, UID, and a group ID, GID, that define what it can access. There are also different secure models: DAC, MAC, capabilities. These models help limit what a compressed process can do. DAC vs MAC vs capabilities diagram. This diagram compares the models. DAC is flexible, MAC is strict, and capabilities give fine-grained privilege control. Understanding these models is essential for Syscall Secure because they define what the process is allowed to do. Measure threats exploiting system calls. System calls can be abused in several ways: privilege, system call, to race, information leaks, denial of service attacks. Attackers often combine these techniques to gain higher leverage or crash the system. Dirty cow, deep breakdown. Dirty cow is a perfect example of a race condition. The kernel checks permissions, but before using the result, the attackers changed the memory mapping. This causes the kernel to write into a protect memory. It shows how timing issue in system calls can lead to privilege escalation. To defend against this threat system use scoped PPF filters, capabilities, MAC framework. These layers greatly reduce the attack surface.
Hello everyone, I'm Yousef Arafa and today I'm gonna represent the last part. SecComp plus BBF filtering. Here we see how SecComp and BBF work together. SecComp decides which system calls are allowed. BBF checks each call's argument and behavior. Together they block unsafe operation and ensure only trusted actions reach the kernel. Monitoring and detection techniques. Advanced monitoring techniques include behavior analysis, and it detects abnormal activity, machine learning, and it finds complex malicious pattern. And the last one is provenance tracking, and it traces the full history of action. These methods help detect attacks early and understand why it happened. Runtime integrity. Runtime integrity ensures the system stays trustworthy, and it includes control flow protection, kernel memory integrity checks, isolation of process and memory regions. These methods prevent attackers from modifying system behaviors at runtime. System call security challenges. Some challenges remain, such as monitoring overhead, container escape, limitation on load devices. These challenges shows why we need a stronger and smarter defense. Future directions. The future of Syscall security includes all AI-based detection, hardware-assisted protection, stronger isolation for containers, lightweight load system call frameworks. These improvements will help secure modern and future systems. To conclude, system calls are essential, but they also create a large surface using strong filtering, monitoring, access control models, and hardware support. Is the best way to keep systems safe. Thank you for the listening. I hope you enjoyed the presentation.